The examination of the universe's inception and its continuous expansion is now at a pivotal stage, with cosmology confronting some of its most foundational uncertainties. A key focus is determining the rate at which the universe is expanding. For over 10 years, two major approaches for measuring this expansion have produced contradictory results. Recent observations of the present state of the universe indicate that the rate of expansion, known as the Hubble constant, is about 9% higher than predictions derived from data from the early universe. Scientists had hoped that the James Webb Space Telescope, JWST, the most advanced telescope ever created, would provide a definitive solution to this issue. However, the new groundbreaking data from JWST has only served to deepen the discrepancy, leading to questions about the validity of the established cosmological model. This has sparked intense debates within the scientific community about whether new physics are needed to modify or completely replace the existing theories that have held for over 4 decades. This possibility is both exciting and unsettling, as it suggests that we might be overlooking an essential component of the universe that could dramatically alter our understanding of its origins. The origins of the universe trace back to the Big Bang, a colossal explosion that in an instant generated energy, matter, and space. From this, the cosmos began as an intensely hot and dense plasma, a mixture of matter and antimatter particles. These particles collided and annihilated each other, but scientists believe a subtle imbalance allowed slightly more matter than antimatter to form, preventing the universe from annihilating itself. Gravity then condensed the plasma, heating it to the point where sound waves, known as baryon acoustic oscillations, propagated through it at speeds greater than half the speed of light. Meanwhile, the dense energy content of the early universe stretched spacetime itself, pushing some matter far enough from the intense heat to survive. As the universe expanded like a balloon inflating, regular matter is thought to have started clumping together around invisible dark matter, eventually forming the first galaxies. These galaxies are believed to be interconnected by a vast cosmic web, linked through dark matter and energy. As the universe continued to expand, both the energy density and the rate of expansion gradually diminished. However, about 5 billion years ago, galaxies began to recede from each other at an accelerated pace, driven by a mysterious force referred to as dark energy. The most widely accepted theory for dark energy is that it behaves as a constant force woven into spacetime itself, embedded in the fabric of the universe's expansion. This force, known as lambda in Einstein's theory of general relativity, maintains a constant density as the universe grows, while the density of ordinary matter decreases over time. Over time, dark energy became the dominant force driving the expansion of the universe, alongside dark matter and regular matter. Together, these forces form the lambda cold dark matter, lambda CDM, model, which describes the universe's evolution and predicts its eventual fate, heat death, also referred to as the Big Freeze. While many of the model's predictions have been confirmed, the nature of dark energy and dark matter remains unresolved. One of the most significant challenges facing cosmology is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield inconsistent results. This discrepancy is so pronounced that it has become one of the field's most urgent issues. Observations from the early universe suggest a higher rate of expansion than the lambda CDM model predicts. These early measurements have been rigorously tested and validated through various observations. According to Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest JWST measurements, the only plausible explanation for the disparity is that our current model is missing something crucial. Measuring the expansion rate of the universe requires more than a simple observation. One of the primary techniques involves examining the cosmic microwave background, CMB, which represents the universe's first light emitted roughly 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped extensively. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB, which shows that the universe is nearly uniform, though slight temperature variations mark areas of higher or lower matter density. These variations reflect the imprint left by baryon acoustic oscillations, which helped cosmologists calculate the Hubble constant, yielding an estimate of approximately 67 kilometers per second per megaparsec. To clarify, this means that a galaxy 1 megaparsec away would recede at 67 kilometers per second, while a galaxy 20 megaparsecs away would recede at 1,340 kilometers per second. If a galaxy were farther than 4,175 megaparsecs away, it would recede faster than the speed of light. Another method for determining the expansion rate involves studying Cepheid variables, pulsating stars whose outer layers expand and contract in a regular pattern as they absorb and release radiation. Discovered by astronomer Henrietta Swan-Leavitt in 1912, this behavior allows astronomers to measure the star's absolute brightness, which can then be used to estimate their distances. The Cepheid variable method, part of what is known as the cosmic distance ladder, has been a key tool for measuring vast distances across the universe. The first step of this ladder involves measuring nearby Cepheids and verifying their distances. From there, astronomers can measure more distant stars and supernovae by observing their redshift. Comparing these measurements allows them to calculate the Hubble constant. In 2019, Rees and his team employed this method to study the Milky Way's closest neighbor, the Large Magellanic Cloud. Their results were startling, showing a significantly higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck data. While the Hubble Space Telescope made significant contributions, its precision was limited in crowded regions of space, causing distant Cepheids to blur with neighboring stars. Some cosmologists have suggested that the discrepancy could be due to measurement errors. However, when the James Webb Space Telescope was launched in December 2021, expectations were high that it could either resolve or confirm the discrepancy. With its 6.5-meter-wide mirror, nearly 3 times the size of Hubble's, and superior infrared capabilities, JWST could observe fainter objects and detect a broader range of wavelengths. Studies comparing Cepheids in the galaxy NGC 4258 to supernovae revealed results nearly identical to Rees' previous findings, with an expansion rate of approximately 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing, returned similar values of 69.6 kilometers per second and 66.6 kilometers per second per megaparsec, respectively. These findings have caused a stir in the cosmological community. As noted by cosmologist Rune Kiffu from the University of California, even a small discrepancy of just 7 kilometers per second is highly unlikely to be a random error, especially considering the precision of the measurements. This has led to a division among cosmologists, with some suggesting measurement errors, while others propose the need for new physics, or a combination of both. Kiffu believes much of the data points toward the necessity for new physics. One leading hypothesis is that dark energy's behavior may have evolved over time. If dark energy was once stronger and has gradually weakened, it could have made the universe appear smaller in its early stages, leading to a faster expansion rate. Other theories suggest the existence of 2 types of dark energy or interactions between dark matter and light, but these ideas come with complexities that many cosmologists are hesitant to accept without more evidence. The discoveries made by the James Webb Space Telescope are not only challenging our understanding of dark energy and dark matter, but are also reshaping our views on galaxy formation. By observing galaxies farther back in time than ever before, JWST has uncovered galaxies that are much more massive and developed than expected, forming just 300 million years after the Big Bang. These early galaxies, which were thought to consist mostly of young hot stars, were found to contain heavy elements and even supermassive black holes at their cores. These findings challenged the traditional model of galaxy evolution, suggesting that the processes of galaxy formation may have been faster and more efficient than previously thought. Furthermore, these findings deepen the mystery of dark matter and dark energy, both of which remain poorly understood despite being dominant components of the universe. Dark matter, which interacts only gravitationally, continues to evade precise detection, prompting ongoing research. Similarly, dark energy, responsible for accelerating the universe's expansion, presents discrepancies like the Hubble tension, raising the possibility that its properties may not be constant across spacetime. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate at different stages of the universe's history. To solve these mysteries, astronomers will need both advanced observational tools, like the James Webb Space Telescope, and theoretical frameworks capable of incorporating new data without discarding the successes of current models. The implications of JWST's discoveries extend far beyond cosmology, touching broader astrophysical questions, including the origins of life and the conditions necessary for life on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets might form around other stars, offering insights into the prevalence and diversity of life across the cosmos. Looking ahead, the James Webb Space Telescope promises to push the boundaries of our understanding of the universe. Its unprecedented sensitivity and resolution will allow astronomers to study the atmospheres of exoplanets, map galaxies in greater detail, and examine the earliest moments of cosmic history with unparalleled precision. JWST's ongoing mission is set to continue revolutionizing our comprehension of physics, astronomy, and our place in the cosmos. Whether uncovering the mysteries of dark matter and dark energy, understanding galaxy formation, or searching for life beyond Earth, the telescope is poised to transform our view of the universe in ways once thought impossible. In conclusion, the intersection of cutting-edge technology, theoretical innovation, and precise observation heralds a new era for cosmology and astrophysics. JWST's contributions will refine our understanding of the universe's origins, challenge established theories, and open doors to groundbreaking discoveries. As we continue our journey of exploration, the universe's mysteries await, and with JWST leading the way, we are poised to uncover the secrets of our cosmic heritage and future. The James Webb Space Telescope offers more than just precise measurements of the universe's expansion and detailed observations of early galaxies. It is positioned to tackle some of cosmology's deepest questions. While the idea that our understanding of the universe could be fundamentally flawed is not new, JWST's precision has sharpened this possibility. Central to the universe's structure are dark matter and dark energy, which remain poorly understood. JWST's ability to study the early universe and observe galaxies that formed just 300 million years after the Big Bang has provided unprecedented insights into galaxy formation. These observations challenged the established theory that galaxies should have taken longer to form, suggesting that processes like star formation and black hole growth may have been more efficient in the early universe. Moreover, JWST's observations are helping to advance the study of dark matter, an elusive substance believed to have played a critical role in shaping the universe's structure through its gravitational effects. JWST's insights may help us understand how dark matter influenced galaxy formation and possibly reveal new characteristics of this mysterious substance. Beyond dark matter, JWST is also assisting in the study of exoplanets and the conditions that might allow life to thrive on other worlds. One of the telescope's main objectives is to analyze exoplanet atmospheres, looking for signs of habitability or even life. By investigating the chemical makeup of these atmospheres, scientists hope to determine the conditions that might support life elsewhere in the universe. This could offer insights into how common Earth-like environments may be. As JWST continues to analyze data, it becomes increasingly clear that we are on the brink of discovering new physics. Whether unraveling the nature of dark energy, exploring the unexpected complexity of early galaxies, or examining the behavior of dark matter, JWST is opening new avenues for understanding the universe. The telescope is not just refining our current theories. It is challenging them, urging scientists to rethink fundamental assumptions and explore new possibilities. These discoveries are pushing the boundaries of physics, astronomy, and even philosophy. As we deepen our understanding of the laws that govern our reality, we are not merely learning about distant stars and galaxies. We are gaining profound insights into the very nature of the cosmos. The questions raised by JWST's findings could lead to a paradigm shift in how we understand the origin, structure, and future of the universe. As we continue to explore the cosmos through the lens of the James Webb Space Telescope, the potential for a paradigm shift in our understanding of the universe grows increasingly likely. The telescope's unprecedented capabilities have already provided a wealth of data that challenges many of our long-held assumptions about the cosmos. For example, the detection of early massive galaxies forming just 300 million years after the Big Bang raises significant questions about the timescale and processes involved in galaxy formation. These galaxies appear far more mature than predicted, suggesting that certain processes, such as star formation and black hole growth, may have occurred much faster and more efficiently than we had previously imagined. This discovery has sparked intense discussions within the scientific community about whether our current models for the evolution of galaxies and cosmic structures need to be revised. Moreover, JWST's study of the early universe has revealed further complexities in the interaction between matter, and dark energy. The telescope's infrared capabilities allow it to peer deeper into the cosmos, examining objects and events that occurred in the first few 100 million years after the Big Bang, a period that was previously beyond our observational reach. These observations are crucial for understanding the role of dark matter, which makes up about 25% of the universe's mass but remains one of the most elusive components of the cosmos. While dark matter doesn't emit light and can only be detected through its gravitational effects, JWST's precision may help clarify how dark matter contributed to the formation of galaxies and large-scale cosmic structures. This is an essential step toward understanding how our universe took shape and how it continues to evolve. In addition to the ongoing quest to understand the fundamental components of the universe, dark matter, dark energy, and galaxy formation, JWST observations are also offering exciting new possibilities in the search for life beyond Earth. One of the telescope's key missions is to study the atmospheres of exoplanets, searching for signs of habitability. By analyzing the chemical composition of these exoplanet atmospheres, scientists hope to detect the presence of molecules such as oxygen, methane, and carbon dioxide, which could be indicators of life. JWST's ability to observe exoplanets in greater detail and with higher sensitivity than ever before could bring us closer to answering the profound question: are we alone in the universe? JWST's contribution to this field extends beyond merely identifying potentially habitable exoplanets. It also promises to help us understand the environmental conditions that might support life. This includes studying the climate and atmospheric conditions of distant planets and learning how these factors might influence the potential for life to emerge. By investigating the chemical interactions within these exoplanetary atmospheres, scientists hope to uncover new insights into the processes that govern planetary habitability, insights that could have profound implications for the search for life beyond Earth.